We move now to considering the effects of viscosity on flows. Up through now, we've been using the Euler momentum equation. The Euler momentum equation is the ideal equation with no viscosity. It takes the form d by dt of the velocity u plus the nonlinear term u dot grad u plus our gradient of pressure divided by density rho is equal to 0. For now, we neglect the potential body forces in the system. This system is the ideal system, the system with no friction, and in particular, no what's called viscosity, which is the friction of moving fluid against itself, the way that fluid rubs and transfers kinetic energy into thermal energy and heat energy of friction. So how do we model viscosity in such a system? Well, we're going to start by just adding a term to the equations and then analyzing what that term does. So this is Euler up here. And let's write a new equation, one that we've modified. So let's write our same right-hand side here, left-hand side, d by dt of u plus u dot grad u. So we're going to have these be the same, plus grad p over rho is equal to now, rather than 0, we're going to write minus 1 over rho times the divergence of a 2 tensor pi ij, where pi ij is called the viscous stress tensor. These two equations are very similar. They differ only in the right-hand side, and we're going to learn a little more about this pi ij stress tensor and what it looks like. But what's very striking is the classes of solutions to the second equation with viscosity are markedly different from those with no viscosity. And in fact, they're so different that we call this a different equation entirely. We call this the Navier-Stokes equation. Though in some senses, it's just momentum equation plus viscosity. All right, so what does this pi ij have? Let's look at the form of pi ij. So first of all, once again, pi ij, this is the viscous stress tensor. And you can tell that this is a tensor and a 2 tensor because it has 2 indices, I and j, 2 independent indices for our tensor. So what's the form of the viscous stress tensor? Well, for now, we're just going to take the empirical form of the viscous stress tensor for a system under Newtonian viscosity. And these are terms we'll analyze and become more familiar with. But for now, let's just write down what it is based on empirically observed properties of viscosity. You can think of this as a minimal set of terms to capture the interactions of shear, which we know should cause friction and slowdown of flow, and eliminating things that we don't expect to cause a slowdown of flow, like solid body rotation style effects. I'm writing this right now in Einstein notation. As a reminder, if a index appears twice in the Einstein notation in a given term, then that indicates summation over all the components. So here we have a k index that's being summed over, but then we have these other indices, I and j, where they only show up once in each of the terms. And these are the independent indices of the tensor that show up here. And each of our terms has both an I and a j. That's our 2 tensor, sort of pointing in 2 directions. And then this term, the last term, it has a summation term in addition to its directional terms, the ij terms. All right. Now, before we proceed further, we can see that there's some terms that look like gradients. There's one gradient here. There's another different gradient here. And then we've got some gradient that's being summed over with something else giving the actual direction. So if we write this in vector notation, just because that can be one we can sometimes get better intuition for, that looks like the following. So in vector notation, pi ij is equal to minus mu times, our first one is the gradient of the vector u. Our second term is the gradient of the vector u, but that quantity transposed turns on its side, and then minus 2/3 of the quantity divergence of u, the contraction of div u, times the identity tensor ij. And this just has a bunch of ones on its diagonal and zeros in its off diagonal elements, and it's the identity. It's the identity matrix as a tensor. Okay, in connecting these terms, if you look at this here, here's our gradient. Grad is d by dxj on ui. That helps you see that this term is the gradient transpose because the I and j have swapped spots compared to this term. So it's the transpose because you've swapped I and j. And then this last term, we can see the contraction here because it's the sum over all the k's. All right. This term, you might ask, where does this come from? The set of relationships, the vector gradient of u, the gradient of u transpose, and then this 2/3 div u identity ij. This comes from requiring that viscosity exists in a flow that has a shear flow, but not a flow that has rotation. So if we draw a flow, like this, a shear flow, we would expect that over time, this part of the flow here is going to slow down and it's going to get pulled back, and this part of the flow here, it's going to speed up and go faster. So in an equilibrated version of this flow, as we go forward in time and allow viscosity to act, we might expect that the fast things would go slower and the slow things would go faster, and globally we'd have just a uniform flow. There'd be an elimination of shear that fits with our intuition of how physical flow happens. So these terms, these gradient terms, they help make sure that where gradients of flow exist, viscosity acts to reduce the gradients of flow because it's negative proportional to the gradients of flow. Now, that's one physical situation. We expect that shear flows should slow down. But the other physical flow that we think of when we're thinking about viscosity is we think about the case of solid body rotation. So this is the case where the flow is fast at the edges and slow at the center, going around in a vortex. And this flow, we expect that something in solid body rotation, it's just in a rotating reference frame with no flow. That's an equivalent statement for solid body rotation. And we expect that a rotating reference frame with no flow, that shouldn't have a viscous force acting to do something weird like change the flow. So this should be constant for all time, ignoring boundary effects. Constant always. So our other terms in the viscosity in the stress tensor are acting to make sure that a flow like this stays constant always, that the sense of gradients of flow only pick up these sort of linear gradients from like a linear shear flow. The other thing that we see for our viscous stress tensor, writing that again, that's pi ij is equal to mu times grad u plus grad u quantity transpose minus 2/3 div u on the identity tensor. But the other thing that we see is we see the viscous coefficient out front, the what's called dynamic coefficient of viscosity. In this special form of the viscous stress tensor, the way I've written it here, this is appropriate to Newtonian fluids. These are fluids which have a few interesting effects. And they're the fluids that we are often used to dealing with in our day-to-day lives. So not all fluids that we deal with are Newtonian fluids. Newtonian fluids have the characteristic that the coefficient of viscosity is a function of the thermodynamic density and temperature only. And for example, the coefficient of viscosity in a Newtonian fluid, so Newtonian, it is not, for example, a function of the velocity field of the fluid itself. It only depends on the thermodynamics rho and T if it is a Newtonian fluid. Additionally, we've neglected something called the bulk viscosity in this viscous stress tensor. That's something that comes up especially in highly compressible fluids. It's related to things like the decay of sound waves propagating in air. But here we've captured the sense of viscosity that leads fluids to come to a halt when they're flowing. And this viscosity gets us a handle on many of the most important viscous processes occurring in fluids.